This conference will now be recorded.
Yes. So just so a very good morning, afternoon, or evening to one and all present here virtually with me today. I'm Resina. I will be here throughout the webinar to help you out technically and organize this webinar successfully. So once again, I will repeat that, how to use the GoToMeetings app and web page, as some of them are new today. So on the GoToMeetings app or web page, you can find 4 icons at the bottom of the center of your screen. That is my camera, screen, and leave. Mic, click on that to mute or unmute yourself. I request you all to stay muted while our speakers are presenting their research work so that it doesn't cause any disturbance to them. Camera, you can use this button to share or unshare the webcam. If you have the option to share the webcam, you can do it, or it is completely your choice. Screen, you can use this button to share the screen. This is the main part during the presentation. After I call your name from my side, I will be making you the presenter, and only when I give the permission, you will be able to share your screen with us. So once I make you the presenter, you can click on the screen button and you will find a pop-up window to share your screen with us. And the fourth icon is the leave, and where you can use this to leave the session. On the top center, you can use the options to change your display settings. At the top right corner, you will have a 3 icons: people, chat, and settings. In the chat option, you can chat with me or any other participants. For the settings, you can use this button to check for the settings for your speakers and microphone. So as mentioned, kindly remain muted during the presentation so that our presenters don't get disturbed. And for any questions or queries, you can ask them in the chat box, or you can ask in the webinar itself. Well, let's not take much of your time. Again, I will finally request you to give a brief introduction about yourself before starting with the session so that we can know about you virtually. So let's move into our session. Our session starts with the oral presentations, but our first speaker, that is from Russia, cannot able to download the GoToMeetings app and cannot able to join due to technical issue. So we have to go to the second talk from Dr. Manish Kumar, that is from Indian Institute of Technology, Mandi, India. And the title of the talk is Functionalized Electrospun Nanofibers for Water Remediation. Hello, Dr. Manish.
Hello.
Yes, so I'm going to
Uh,
make you the presenter. Yes. So please share your screen. So we can able to see your screen. Yeah.
uh,
Yes.
is
Can you
this?
make it a full screen?
Yeah, 1 minute, please.
Uh,
Is it now visible to everyone?
yes, yes, it is visible. Okay, but there is a disturbance from your side. The sound is coming. Can you please check so that
Okay,
it
I'll
will
ask
be
to them. Yeah, I'll ask them. Hello.
okay?
Yeah. So
Yes.
now it is okay with the all,
Yeah.
right?
Yes, everything
So
is
I would
okay.
like to thanks to organizers and thanks uh, to you for this kind words for introduction. So today I'm Manish Kumar from Indian Institute of Technology, Mandi, India, and I'll be speaking on electrospoon mat, functionalization of electrospoon mat and its applications for water treatment, wastewater treatment and remediations. So basically in India, we are having this IIT and we are having 2 campuses in the lap of Himalayas, North Campus and South Campus. This environment is very, very good and beautiful campuses we are having, and it's very good for the research. So I will not waste much time onto these things. I'll be speaking on the electrospin mat. So basically, it's not moving. Okay, so according to WHO report on water pollutions, so we can see that in 2017, almost 71% of global population was able to take able to manage the drinking water services. But according to 2020 to 25, half of the world's population will be living in the water stressed areas, And if you can see the data also, that almost 4,85,000 people deaths due to diarrhea, and which is caused by the polluted water. And in at least developed countries, 22% of healthcare facilities have no water services, and 21% no sanitation services, and 22% no waste management. Uh, so because of these things, we have to think about it, and we have to treat the water, we have to purify the water. So according to this, if you are able to see this, according to this map, top 20 cities of the world are facing the problem of water, including India, and including the developed countries also. We are having a water problem in every top cities, in top 20 cities of the worldwide. And these top 20 cities are like these defined as cities that use at least 40% of all available water from the watersheds. So, and now if I'll talk about the India, in India, 54% of India faces high to extremely high water stresses. So in India has the total population of 17% of the world population, and but has only 4% of water. India became the water stressed nation because of the rising population and urbanization. And almost 21% of all diseases in India are caused due to the drinking water, and 5% of India's fresh water resources available only for the municipal uses. And remaining all amount goes to the industries and agriculture. If we will talk about the earth, like this, we are having 97% water in the oceans, and that is not for useful, that is salty water. And this is the something that we need. We can purify the water, and we can fulfill the requirement of the population, because we are having only 3% of the fresh water, and that 3% water is also like out of that 68% of that water is in ice caps, in glaciers. So that is not reachable for the humans, and we cannot use that. And we are having only 30% of that water as a groundwater, and 1% as a fresh water, like surface water. This only we can use. So in that case, we have to think about this oceans water. We have to purify that water, and in that matter, we are working to purify this water. First of this, before that, I'm going to the topic. First, I'll explain the things that what cause the pollutions in the water. So, like these animals, farms and lawns, and in residential neighborhoods and urban streets, and then industries. These are the major cause. They are producing pollutions in the water bodies, and we can minimize that things, and we can like we can fulfill the demand of water pollution just to purify the water. So these are the conventional techniques. Like earlier we were used to these techniques, but there are some limitations, like very high energy requirements, high expensive, and then required large surface area for land, water quality get affected, and efficiency is very low. So these are the few conventional techniques like screening. So in screening, we can remove only the floating matters, and aeration. So in that we can remove the taste, odor, and dissolved gases like CO2, S2S, and dissolved oxygen. Then plain sedimentation can be remove only the suspended impurities, and then sedimentation with coagulation. In this, we have to add some chemicals. With that, the particles will be heavier, and then we can remove them out. Then filtration. So basically, I am working on the filtration part. So we fabricate the membranes, and then we use it for the different applications for water purification only. So these limitations made us to like need of the membrane requirement. So need of the membrane technology for water purification. Basically, we are fabricating the nanofibrous based membranes. So in that case, we can minimize. In that case, what we can do is the membranes are having high surface to volume ratio, higher mechanical stability, and they can be operated at atmospheric pressures. and these physical, chemical, and electrical properties also can be tunable. So advantage of these membranes are like no complex instrumentation, no large energy requirement, no more large land requirement. So they made us like this technology to favorable for the in all conditions. So basically, if you will think, if you will see about this membrane system, it is like we are having this three-layer structure. Some one is porous structure, that will be the support layer. Then this nanofibrous membrane, so it is basically nano filtration. So this bacteria, germs, fungus, and impurities like heavy metals, colors, this all can be removed from the using this membrane technology. It will allow only to pass the water molecules only. So next is how to fabricate these membranes. So basically there are four techniques: phase inversion, electrospinning, track etching, and interfacial polymerization. In phase inversion, track etching, interfacial polymerization, we can make a porous membranes, but before that we have to make a film, then we have to create the porosity into it. So these are having some limitation again. Then the energy requirement, cost effective, like these things can be like other things. So due to that, we are using electrospinning technique. So in electrospinning technique, basically there are three phases. In first phase, we are first we have to make the solution. We have to prepare the solution. In solution, we can control three parameters like viscosity, conductivity, surface tension. So basically viscosity in this first graph, you can see if you viscosity is very less, then you cannot make a fibers. Then you will find the beads formation on the collector. So this is the something that you have to optimize. This viscosity should be optimum. So if you increase more than a optimum viscosity, then also there is a problem. So fiber diameter will be more, so you will not get a nanofiber nano dimensions fibers. And then next is conductivity and surface tension. These also plays a very important role to it. And then second phase is the spinning parameters. Spin.
25 dakika sonra olayım. İyi misin? Nasılsın? Tamam.
Hello. Hello. Am
Bir
I audible?
görüşelim.
Yes, you are
Bir
audible.
görüşeyim ben hocam. Dur bir şeyim sıram
Some
geldi.
sound is there. Okay. Sorry for this interruption, like interference. So next is electrospinning conditions, applied voltage and
Tamam.
feed rate and tip.
Kapatıyorum hocam. Birazdan tamam. Teşekkür öptüm. Hadi bay bay.
Hello. Hello.
Hello?
Yeah. Someone is asking something, or something was.
Let me check. Hello, Dr. Delia.
Yes.
Yes, can you please unmute yourself because there is, like it is disturbing the presentation.
I am sorry.
Okay. Yeah, please continue, Dr. Manish.
Okay, so next is the electrospinning conditions. So applied voltage, feed rate, tip to collector distance, and concentration. So basically in schematic diagram is like you can see into it. First we have prepared the polymer solution like this solution, and then we feed this solution into the syringe pump, and then we apply a high voltage on the tip of the needle. So basically when you apply the high voltage here, and this collector is grounded, so this area here electric forces plays a important role. So when this electric voltage applied, then cone formation will be there. This is known as the Taylor cone formation, and then this is stretching out, and these fibers deposit on the collector, which is grounded. So basically applied voltage plays an important role. So like you can see in this figure, when you increase the voltage, the diameter of the fiber reduces, but at a particular point, if you increase very high voltage, then the fiber length will be very short. Like then you will get a broken fibers, you will not get a continuous fibers. So next is feed rate. So feed rate is something like flow rate, and if you increase the flow rate, then the diameter of the fiber will increase. So if diameter of the fiber will increase, the surface area of the your membrane will reduces. And next is the this something like distance tip to collector, this distance from needle to the collector. So when you increase the distance, you increase this distance, like your fiber has to travel more, so in that it will stretch more, so the diameter of the fiber will be reduced. And then the ambient parameters and the temperature also plays an important role. So now the application of the electrospin nanofibers. So basically now people are using these nanofibers for different applications, like for filtration, tissue engineering, wound healing, energy storage, sensors, and catalyst and enzymes carriers. And I am working on the filtration part, so I am using these nanofibers as a filtration and as a biomolecule sensors. So electrochemical sensors I'll be talking about in these two topics only, sensors and filtrations. So like functionalized electrospin nanofibers. Basically, there are 3-4 types like by which that you can functionalize your nanofibers. First thing is we are having a polymer solution. Into that, in polymer solution itself, you can add your functionalized groups like metal oxide nanoparticles, MOF, COF, covalent organic frameworks, and metal organic frameworks. Whatever you want that functional group, that you can into the polymer, and then you can electrospin that polymer itself. Then you will get like this kind of fibers. In fiber itself, you are having your functionalized group as well as on the surface, as well as in the inside of the fibers also. And you can make hollow fibers, like if you are having two polymer solutions, so inside polymer, after formation of the nanofibers, you can dissolve the inside core, and you can get the hollow nanofibers. And third thing is like one by one. So first you have to mix polymers also you can use, and you can use like first you can make one membrane, and then onto that you can do another membrane also. Third thing is like first you have fabricated your nanofibers using like electrospinning. Then you activated the sites onto the fibers using some activators, some other solvents, and then you can add your targeted group onto it, and that you can use for the particular application. And third thing, last one is like first you have fabricated your nanofibrous membrane, and onto that you can coat another nanofibers, cross linking nanofibers or some other nanofibers also. So these are the some methods by that you can functionalize your nanofibers. So now I have fabricated this nanofibers alpha-203 nanofibers membrane. So into it we have made it using PAN, polyacryl nitrile nanofibers, nitrile, and we added alpha Fe23 into it. So in during electrospinning itself, we have functionalized it, and in the same image you can see that very fine nanofibers, almost they are having 100 to 300 nanometer size in diameter. And these fibers we used for adsorption of methylene blue, methylene orange, and for heavy metal adsorption, copper and lead we used it. And it shows a very good efficiency towards lead and copper heavy metals, as well as for colors. And then again we used it as a electrochemical sensors also for paracetamol and ascorbic acid. So in this video you can see how to make the these nanofibers. So here we are having this tip electrospinning needle. This is needle, and here we are having a collector. So we can electrospin it onto nanofiber, and then this in this figure you can see that we are able to make very good membrane, like films kind of membranes, and we further use these membranes for water purification systems. So as you can see, then we have validate its structural validation. For that we have first we optimized it with different concentrations of alpha-203. So we found that some constant 3% of alpha Fe2O3, we found that it's showing very good fine nanoparticles. As you can see in figure A, it's fine, but it's pure 10 nanofibers. In B, at some concentration, it's giving beads formation with the iron. And in C, it's a optimized concentration, 3% of alpha Fe2O3. It's showing a very good fine nanoparticles, fine nanofibers. And if you increase further, then the diameter of the nanofibers also increases. Then structural validation, we have we functionalize membrane with different things. Like first we functionalize. This is A is showing XRD for the pure pen nanofiber. B is showing for pen plus alpha Fe2O3. C is showing pen plus CaCO3 calcium carbonate. We have grown the crystals on the nanofibers film. And then D again we have coated it with cellulose triacetate. And then in TEM image you can see this like different carbon, nitrogen, oxygen, and iron. It's all are uniformly distributed on throughout the fiber. Then FTIR also we will able to see the iron footprints onto it, and some other functional groups like carbon, oxygen, and OH hydroxy bonds like this. And then we went for the thermal stability of this membrane. So we want to use this membrane for a water purification system. So we have seen that this membrane was very much stable up to 250 degrees centigrade, from room temperature to 250 degrees. So in this, like you can see 250 to 450 degree, there was a onset at around 250 degree, and complete degradation was around 450 degree, and there was 5% was remaining, that was due to maybe alpha Fe2O3 and CaCO3. So this membrane shows that we can use it up to 250 degrees centigrade, and this is our parameters. We want to use this membrane as a water purification system, so that suits on our range. Further, we checked its surface hydrophilicity. The membrane should be hydrophilic in case of filtration. So pure pen nanofiber shows a hydrophobic membrane. It's around, like you can see, its contact angle was 110, and when we added alpha Fe2O3, it was reduced up to 56 degree after just after 1 second. And then when we added CaCO3 and CTA onto it, it reached up to 14 degree only. Then we checked its membrane stability in different acidic and basic mediums. Like wastewater can be acidic or basic. So we tested this membrane for different mediums. As you can see, that membrane shows almost stable into different acidic and basic mediums. Like from 3 to 11 pH, there was no mass loss. Up to and in different solvents also, it's showing very much stable. Like there was no much loss into it. Then we tested its magnetic and tensile strength mechanical properties. Then we found that it shows a magnetic behavior also due to alpha Fe2O3. So this is the good thing. Like if we after something we want to separate it out, the membrane after adsorption, or if we dip this membrane into solution, then also it can be filter out, like it can be separated out using the magnetic properties. And we found that after this functionalization, the tensile strength also increases. So this was the basically setup, like not setup, like this is the lab scale. And we have made a prototype also, and we filed a patent also for this, and that patent is in the process now itself. And this we used a different concentration of dyes, methylene blue 20 ppm, 10 ppm, and after filtration you can see the color, it's very much clear, almost 99% removed from the water. And for higher concentrations also we tested it for 200 ppm, and we found that it almost 95% efficiency for the higher concentrations. So in this video you can see we are just putting some drops from methylene blue solution onto this membrane, and into this beaker, we got a very fine without purified water without any colors. So this was the membrane basically, and we put it into the conical flask, and then we tested it. So the mechanism was like this is L523. It is having when we this is methylene blue dye degradation. So when we applied a visible light onto it, then the electrons of the valence band went to the conduction band, and then this oxygen comes with this. Then it creates a free radical oxygen. So that will that react with the methylene blue, and it produces CO2 plus H2. And same thing happens in the valence band also. Like OS radicals will formation will be there, and it produces methylene blue CO2 plus S2 with this methylene blue. As you can see, with the time, with respect to time, in almost 240 minutes, it was able to degrade almost 98% methylene blue. And if we can compare with the pure pen nanofibers, pure pen nanofibers was able to remove almost only 38% dyes from the nanofibers. Then after that, we tested it with the photocurrent also. Then when we turn on the light, it was showing 3 microampere, and when we turn off the light, it went to 0. So it was showing the activities, photo activities also. So further we used it as a electrochemical sensors also. So then what we did, first we calcined this material. So we removed the polymer, we got only the L523 nanofibers, and then we coated that nanofibers on the GC. So we used this electrochemical system, 3 electrode system into it. We are having AgAgCl as a reference electrode, platinum as a counter electrode, and then GC, grassy carbon electrode, as a working electrode. On grassy carbon electrode, we coated our material, this L523 nanofibers, and we found that into this, you can see that there is a enhancement into the current, as well as in oxidation, as well as in reduction for the coated GC. And after that, we found we tested it for a paracetamol sensing, and as well as for ascorbic acid. So because in during this corona COVID time, there was intake of for this paracetamol, as well as the vitamin C, ascorbic acid also there. So there was a very much pollution in this hospitals waste, and for this paracetamol and ascorbic acid. So to detect that things, we used it as a sensor. So we found when we increasing addition of the serial addition of the ascorbic acid as well as the paracetamol, we found that current of the anodic and cathodic both currents increases, and we found that it was showing 1.3 microampere per micromolar per centimeter square sensitivity for paracetamol, and 18.3 microampere for the ascorbic acid. And the limit of detection was 2.83 micromolar and 0.283 millimolar for the ascorbic acid and this paracetamol respectively. Then further we use this membrane for the antibacterial studies. So first we use this antibacterial for the E. coli bacteria. So in that you can see that first we have controlled experiment into it. So we grown the E. coli bacteria on 2 vials. In first vial there was no material, and in second vial there was some membranes, like alpha-23 membrane was there. So in A and B figures, you can see that there was too much growth of the E. coli bacteria, but in C and D there was no growth of the E. coli bacteria. So we found that this membrane was very much efficient for for antibacterial properties. Further, this membrane shows a very good heavy metal adsorption capability also, and we found that the maximum adsorption capacity for copper and lead was 153 milligram per gram, and 184 milligram per gram for lead. In this XPS also, you can see that figure A and figure D. In A, we are having only Fe2O3 and calcium carbonate with on our membrane. Then we used it for the heavy metal adsorption, and then you can see there was a peak for the lead and this copper as well. So in then deconvolution also, you can see there was a reduction and of FeO peak, and then into figure C, and then increases with this F. So what happens, like CO3 peak, earlier it was CaCO3, and then CO3 reacted with the copper as well as with with lead. So there is a bit change into the binding energy. So there is a very small like shifting into binding energy with it. So we confirmed it with that. Then next is we found we checked it with methylene orange and methylene blue degradation, and we found that this membrane was able to degrade the methylene blue more efficiently compared to methylene orange. So I would like to acknowledge my supervisor, thesis supervisor, Dr. Jaspreet Kaur Randhawa, and AMRC, Advanced Material Research Center at IIT Mandi for characterization facilities of this membrane, and NMHS, like National Mission on Himalayan Studies, for funding this project, and my lab members. So thank you.
Yes, thank you, Dr. Manish, for your presentation. So, any questions from anyone? Okay, no questions. Thank you once again for your presence and presentation.
Thank you very much.
Thank you. So, our next presenter is Dr. Manojit Dev from Coalesce Group of Colleges, India. And the title of the talk is Tailored NiFe2O4 Nanostructure Synthesis Structural Vibrational Magnetic Study. Hello, Dr. Manojit. Are you ready with your presentation? Yes, you are the presenter now. Please share your screen with us. Hello, Dr. Manojit.
Please make me the presenter here.
Yeah, you are the presenter. Please click on the screen icon on your screen. Is there any issue, Dr. Manojit? Hello, Dr. Manojit. We can able to see your screen, but your mic is not connected, so we cannot able to hear your voice. Can you please once check, because here it is showing that you are not connected to your audio. We can see that you have opened your mobile phone through which you are going to present. So I think he cannot, there is just some technical issue. So please allow me a moment. I will contact Dr. Manojit. So I just contacted Dr. Manojit due to some internet issues, so he cannot able to present now. As the next speaker is also not with us, we'll go to the next presentation from Dr. K.S. Joseph Wilson. Hello, Dr. Joseph. Are you ready to give the presentation? Hello. Hello. Mhm. Hello, Dr. Wilson. Hello, Dr. Kamraj. Can you able to give the presentation now?
Yeah, yes, madam. Yes, madam.
Yes, thank you very much. But as he left the session, so we will continue with your talk. So our next presenter is Dr. P. Kamraj from Bharat Institute of Higher Education and Research, India. And the title of the talk is Enhanced Hydrogen Evolution Using CO2 ZnSnSO4 Nanoparticle Decorated with CO2 as Noble Metal Free PN Heterojunction Photocatalyst. So I'm going to make you the presenter. Yes, so please share your screen with us.
Madam, for me, it will take some 10 minutes, 15 minutes, madam.
Okay. We will continue with Dr. Kamraj presentation. After that, you can present.
Yes, I am ready. Okay, thank you, madam.
Okay,
Thank you.
thank you. Yes, we can able to see your slide. You can make it a full screen.
Yeah.
Yes, perfect. Please continue.
Good day to one and all. I am Dr. Kamraj, Dean Science and Humanities, Bharat Institute of Higher Education and Research, Chennai, India. So I am going to discuss about the the topic enhanced hydrogen evolution using copper zinc tin sulfide nanoparticles decorated cerium oxide as a noble metal-free PN heterojunction photocatalyst. So an overview of this is we are going to see the needs, global needs for the for energy, the alternative solutions for it, and what is the current work done on hydrogen energy production. Actually, we are need of a lot of energy, and the fossil fuels are getting depleted. So we are in the era of finding the alternative fuels. This is the graphical representation of world energy demand in terms of fuel type. So it involves oil, gas, coal, and also the renewables. So the year-wise comparison you can see. So every year the demand for energy is getting increased. So we have a lot of energy sources, which include nuclear, coal, water, biomass, natural gas, oil, and also the solar power. But at the same time, we are running short of the fossil fuels. So if you look at the statistics say China and the US are the top users of fossil fuels. So that is the actual scenario, whereas the other countries do use the fossil fuels, but compared to them, less. So the disadvantages of fossil fuels are the low energy density of the fossil fuels, and there's also the danger of explosion. Then the harmful byproducts produced during combustion reaction, the fuels are produced, and the air pollution, the subsequent carbon emissions, all these issues are there. So the carbon dioxide emission is a great problem, resulting in global warming that we all know. So that again results in the climate change. So the climate change occurs or is the result of the day that we see throughout the universe. So that is a very important impact of burning the fossil fuel. And apart from that, the ozone layer depletion is also equally important in terms of environmental protection, and also the acid rains and the other problems. So the depletion of oxygen, which is very much the oxygen, which is very much required for the survival of the living organisms. So that's a share of carbon dioxide by the countries that this diagram is a representation of the share of carbon dioxide or carbon emissions to the atmosphere. So you can see, you can have an idea about. So now we are in a situation that we need to find alternative use of energy, alternative methods. So the hydrogen market is there, and we are supposed to go for using the hydrogen as a fuel. So the hydrogen is hydrogen to be used in different requirements. So the hydrogen markets, according to statistics, $100 billion per year, statistics say. So all these industries also involved. So the advantages of the hydrogen, why we should go for hydrogen energy in the present situation, because it's an excellent energy carrier. So 142 mJ per kg. So clean, we can use it diversified, use as domestic source, economically competitive. So it has better security than even the commercial fuel safety, in terms of safety aspect also is positive in case of hydrogen energy. So we have the flexibility of using hydrogen energy. So the energy source materials for hydrogen production are listed here, include natural gas, propane, biomass, etc. And so if natural gas or propane is used, this involves some associated requirements, reformation using carbon-based fuels, electrolysis using electric sources, then if you use solar electrolysis using carbon-free electric sources, and also you can use uranium. So there the nuclear waste is generated. So thermal dissociation is also possible through thermal solar thermal sources. So this is the distribution of various sources. So now coming back to the current research work done by my team, which is on quaternary CZTS nanoparticle decorated CO2 as a noble metal-free PN heterojunction photocatalyst. So this helps in getting efficient hydrogen evolution. So this involves the use of silver nitrate, cerium nitrate, PVP. They undergo when they undergo solvothermal treatment, a solvosphere of CO2 be obtained, and that the solvothermal growth of CZTS can be done further. So CZTS CO2 composite is synthesized this way. So the characterization was done XRD. So the XRD was examined. XRD was done by compact alpha radiation at a voltage of 40 kV. So the morphology and the TDS mapping of the sample was observed by field emission electron microscopy. So the FECM, the SEM image of CO2, CO2 exhibits a holosphere morphology, and the SEM image clearly reveals the fact CZTS has non-uniform spherical morphology that you can see, and the VLAX mapping. So this is the energy parameter, PL spectra. From the Raman spectra, a strong Raman band appeared at 470 cm inverse for both the CO2 and CZTS. It corresponds to F2G Raman active mode of cubic structure CO2. Whereas in contrast, CZTS and CZTS CO2 T minus exhibit intense peaks at 283 and 332 nanometer, cm inverse, and also 364 cm inverse. So this suggests the existence of tesseract CZTS. So the Raman spectra don't contain impurity peaks like Z and SNO3. So that is confirmed here. the CL spectra there. So the recombination rate of photo-induced excitons can be measured by using PL analysis. Usually describes the PL emission intensity, and it is the inversion of charge recombination rate. So the figure shows PL spectra of CO2, CZPS, and CO2 -1 composite, CZPS CO2 2 minus composite, and CZPS CO2 3 minus composite, and also CZPS CO2 4 minus composite with an excitation wavelength of 330 nanometer. Where CO2 shows two strong blue emission peaks at 391 nanometer and 468 nanometer, which may be due to the band gap energy of 2.98 electron volt. So the high intensity emission peak is attributed to its high recombination rate of photo-generated electron volt bands, which is due to the defects of surface of the CO2 holosphere. So the high surface charge recombination rate conveys an opposite effect on photocatalytic activity of bare CO2. So therefore, the modification of CO2 surface with CZPS plays an essential role in the charge recombination process. So the emission intensity further decreases with increase in loading amount of CZPS. So hydrogen production efficiency could be seen in this diagram. So photocatalytic hydrogen generation mechanism. So the experimental results show that CO2 surface modification with the CZPS plays a significant role in the hydrogen production reaction. So we propose a significantly developed and possible hydrogen evolution mechanism. In this mechanism, electrons and holes transfer based on the band structure of semiconductors. Therefore, band and conduction band edge positions before being in contact with each other can be calculated by following the a mathematical relation EVB is equal to x minus EC plus 0.5 EG, and ECB equal to EVB minus EG. So this mathematical relations have been used here. So the photo current measurement. So this work has been published in New Journal of Chemistry in 2020. So this is the comparison table between the photocatalyst and the photocatalyst and the reaction condition, what is the rate of hydrogen evolution, and we can when we compare these different catalysts, we could see our CZPS CO2 using light source the whole scavengers, namely sodium sulfate and sodium sulfide. The hydrogen evolution rate is 2.93. This is what seen. So very visible advantages. So the conclusion of this study is a noble metal free CZPS CO2 composite PN heterojunction catalyst has been synthesized using salvo-thermal method, the hydrothermal method. So nanoparticles are uniformly coated. It has been observed onto CO2 under two hydrothermal conditions. So the existence of quaternary CZPS interfacial contact was confirmed with the XPS and the It's also demonstrated that by increasing the loading amount of on the surface of the CO2, hydrogen production rate has been observed to be higher than that of trans CO2 and even higher than CZPS. So the excellent performance of the composite is ascribed to the synergistic effect between CO2 and the CZPS. So it's reproducible. And, we can go for further photocatalytic applications too. So this will be, I think, this catalyst or this system could open the other, result in further openings and research for further studies on such composites or similar composites for higher energy production rate. So these are some of the references. Thank you.
Thank you, Dr. Kamaraj, for your presentation. So any questions from anyone? So no questions. Thank you once again for your presence and presentation.
Thank you, madam.
Yes. So as the Dr. Rajesh Sheikh BB from Homi Bhabha Center University, India has arrived to the webinar. So hello, Dr. Sheikh. Hello.
Hello, madam.
Yes, will you give, sorry, Dr. Joseph, can I ask
Uh,
Dr. Rajay has already arrived. I will once ask him whether he will give the presentation or not.
thank
Hello,
you. Thank
Dr. Sheikh. Yeah, can you please unmute yourself, Dr. Sheikh? It is showing that you have muted yourself. Yes. Hello, Dr. Sheikh.
Hello.
Yes, so I'm going to make you the presenter. Yes. So please share your
Yes.
screen with us. Yes, we can able to see that your screen. Please open your presentation. Please click on the screen icon on your screen. That is the third one. Hello, Dr. Sheikh. Am I audible to you? Dr. Sheikh, there is a lots of disturbance of sound coming from your side. Hello. Hello.
Hello.
Yes, doctor. Am I audible to you?
Yes, yes, yeah.
Yeah. Can you please start the presentation?
Hello.
You can do one thing. We cannot able to hear your voice. You can plug your
Yeah, yeah.
earphones with you. We will go to other presentation. So once you are free, we can schedule your talk because there is a lots of sound coming from your side.
Yeah.
Yeah. So you can plug in your earphones. We'll go with other presentation. In the meanwhile, you can set up your earphones and let us know. We will schedule your talk. Yeah. So hello, Dr. Joseph. Can you able to give the presentation now?
Yes, madam.
Yeah, because as we can see, my voice is not audible to Dr. Sheikh. So we'll
Okay.
go with your presentation. So I'm
Okay,
going
madam.
to make you the presenter.
Oh,
Yes. So please share your screen with us.
okay.
So our next presenter is Dr. K.S. Joseph Wilson from Madurai Kamaraj University, India. And the title of the talk is Realization of Magnetostructural Coupling and Giant Magnetocaloric Effect in Off-Stoichiometric MnCOG alloys. So we can able to see your presentation. You can make it a full screen.
Yes, 1 minute.
Yeah, hello, Dr. Joseph. You can open your presentation.
Is it visible now?
We can able to see the desktop, but not the presentation. You have not yet opened it.
Is it okay, madam, now?
No, the presentation is not visible. I think you have to close one screen share and again try to open that because you have not enabled to see the presentation. It is only your computer screen we have. I mean, it's visible.
So this is actually what?
You have to share the presentation as well.
1 minute. So here,
So once you close the screen sharing,
oh, okay. Screen sharing.
yes.
Yes.
Yeah,
Yes.
again click on that.
Screen.
Yes.
Now share.
Yeah, now share the presentation.
Now it's okay.
Yeah, now it is perfect. You can make it a full screen and start presenting.
The full screen is it
Yeah,
gives
go to
some problem.
slideshow.
Go to slide.
In the upper toolbar, you have a slideshow option.
1 minute.
Hmm.
Slideshow bar is
Yeah, on the left side, on the
this
upper
side.
toolbar. Yeah, you
This
can
is
see insert, draw, design, animation, slideshow in the orange color part.
here.
Yeah, go to left side.
Left side corner.
Yeah, more left side. Yes.
I think
Left side, not the right one.
class. This is actually
On the top left corner, you have, yes, more left.
hmm, it is not coming actually. More left corner, 6 dots are there.
There is no dots. Yeah. You can see the heading is there, right? Webinar USA - PowerPoint.
Yes,
Yeah, below that slideshow is there.
1 minute. One minute. No, it is actually hidden actually here.
On the top arrow, top one. Yeah.
Now keep see the screen.
Yeah, what you can see in the, yeah, that you can on the, your name is written, right? Joseph Wilson.
Yes,
You
here
can
it is.
see that. Otherwise, you can continue like that, no issue.
Okay, okay.
Yes.
I will try once again, otherwise I will continue.
Okay.
May I close and then again open? One trial.
Yeah, you can close that and once again open, no issue. So you can click on that option as well. Yes,
Okay.
perfect. Yes,
Okay.
yes.
Thank you very much. Actually, my topic is tuning of photonic band gap for one-dimensional photonic crystal as an intermediate reflect layer for photovoltaic applications. This is my topic. In the previous one, it was mistaken. Now it is okay.
Please click on the right side arrow. Yes.
Actually, the photonic crystal is based on refractive index of the medium. The refractive index we can define in so many factors. Actually, it is actually the nature of the substance. We can express in terms of permittivity and permeability. The permittivity and permeability are the key factors, parameters of all the substance. Actually, the square root of epsilon or mu r gives the refractive index. And also we can define using Snell's law, n equal to sin I by sin r. The angle of incidence and the angle of reflection is also based on the refractive index. And also we can study from the velocity of light and the velocity of the medium, n equal to c by v. So we know that c is the highest velocity in nature, light in nature. V is the velocity of light in medium. So always refractiveness is greater than 1. So like this, the refractiveness based on so many factors, it actually, we can say that it is the nature of the substance. So based on the things only, we can arrange photonic crystals. We have come to know the electronic p-n junction crystals and everything. There, the major one is band gap. So here also, there the band gap, there is no propagation of electrons. So the band between valence band and conduction, as we have already familiar with that. So similar to electronic crystals, we have photonic crystals. Here it is mainly based on photonic band gap. In that gap, there is no propagation of light. Light cannot be propagated in that frequency range or wavelength range. Therefore, we can call it as photonic band gap. So based on the photonic band gap, we can define or design so many crystals called photonic crystals. So here also we have the 3 types of photonic crystals. One is one-dimensional photonic crystal, two-dimensional photonic crystal, and three-dimensional photonic crystal. The one-dimensional photonic crystal, we can have an array of high refractive index layer and the low refractive index layer in a particular directions. We can call it as only one direction, one-dimensional photonic crystals. So on the other hand, if we arrange the high refractive index layer and low refractive index layer in two directions, we can have two-dimensional photonic crystals. Otherwise, when we have three dimensions, we have three-dimensional photonic crystals. So everything is based on refractive index. The refractiveness of the medium, here we are taking that one high refractive index layer and another one is low refractive index layer. This combination makes a photonic crystals. It will create photonic band gap. That is a forbidden band gap of some frequency range. So like this, we can have three types of photonic crystals. Now we can also see naturally occurring photonic crystals. Naturally occurring photonic. See here we have so many natural things: peacock feather, and then so many insects and fish. So these are producing some sort of colors. So actually we can call this as photonic crystals, naturally occurring photonic crystals, because that light is forbidden through that material, the living beings. Therefore it is reflected. We can say that it is very beautiful. We can say that it is naturally occurring photonic crystals. So I already told you that the basic of the photonic crystal is photonic band gap. Here I am giving one example. Propagation of light over a particular wavelength range is forbidden, called photonic band gap. Here in the y-axis we have reflectance, x-axis we have the wavelength in nanometer. So from 1200 to 1600 around, the light is completely reflected. So there is no propagation. So we can call this as a photonic band gap. We can call this as a photonic band gap. So this is the backbone of all the photonic crystals. Where is the gap? How to tune the gap? So when we tune the photonic band gap, we can do wonder in all the areas, not only in scientific areas, medical, and also defense. So in all the areas, we can, by tuning the photonic band gap, we can apply to so many other applications like electronics. So but when we compare the electronic component, so in so many areas photonic crystals has more advantage, because the carrier is photon. There the carrier is electron. Photon has highest velocity in nature than the electrons. We know that photon is a chargeless particle. Here electron is a charged particle. So here the photon has no mass, only carrier, energy carrier, but electron we have mass. So like this we can have so many advantages. So we can use photonic crystal for so many displays. Nowadays we have LED and so many things are there, instead of getting some electronic components. So now how to tune the photonic band gap? Here this aim of this topic is, based on photonic crystal, we can have magnetophotonic crystals. By using magnetophotonic crystals, we can apply for anti-reflection coating or inter-reflective layer or some other layer in solar cells. It can be applicable to all the other scientific and industry area, but here we are analyzing how to use this magnetic photonic crystal in solar cells. So for that purpose, we had to tune the photonic band gap. So the tuning of photonic band gap is so many ways are there. So here we are briefly studying some of the arrangements. So the novel one-dimensional magnetic photonic crystal having magnetic nanocomposite medium consists of yttrium iron garnet. Here we are taking Ig and silver as high refractive index. This composite layer as a high refractive index layer, and air as the low refractive index layer. It is theoretically designed. So we are taking two materials. One is a composite material, composite material. We can call it as nanocomposite material. Here the base material is yttrium iron garnet, and then there we doped silver nanoparticles. Therefore, we can say that it is a magnetic nanocomposite. This magnetic nanocomposite medium is taken as A medium and air as the B medium. So it is first one is a high refractive index layer, and second one is a low refractive index layer. So by using this, we can make a one-dimensional photonic crystal. Then the transmission properties of the one-dimensional photonic crystal is studied by using transfer matrix method. So many methods are available nowadays. for studying the photonic band gap. So here we have studied the transmission property using transfer matrix method. Then the photonic band gap is we can calculate by applying the external perturbations like magnetic field, filling factor, number of layers, and so on, etc., etc. So this is the one-dimensional photonic crystal. Is theoretically designed periodically arranging silver doped naval magnetic nanocomposite system as A layer and B as a B layer. So see here. So this is the one dimension. If you have arranged in a particular direction for n period, it may be 10 or 15, whatever may be, according to our convenience, according to our need. We can have the one-dimensional photonic crystal. A medium, a magnetic nanocomposite medium. B medium is the air medium. So theory. So here we have magnetic nanocomposite medium. So we want to find the refractive index. So for finding the refractive index, first we should find the permittivity of the medium. Permittivity of medium. So for this nanocomposite medium, it possesses also permittivity as well as permeability. Here we are using Maxwell-Garnett equation, the famous approximation Maxwell-Garnett equation. By using this, we can find the permittivity of medium, and also using this formula, we can find the permeability of the medium. Now we know that by taking a permittivity and permeability, we can get the refractive index. So by using all these equations, we can find the permittivity and permeability of this medium. Then we can find the refractive index. By substituting the refractive index in the matrix format, we can get. So here it is given delta I is equal to omega by c n1 d1 cos theta 1. The incident angle d1 is nothing but thickness ni. It may be Na or Nb. Na means a nanocomposite medium, Nb is the air medium. So by substituting this, we can get delta. By using this delta medium, we can get individual matrix. Then by forming this matrix, we can get that we can analyze the transmission properties using the transfer matrix method. All the things are given. C is the speed of light, Ny is the refractive index, D is the thickness of the layer, theta is the angle of incidence of the layer. Actually, we are taking normal incidence, therefore we can get cos theta is equal to 1. Now, by finding this, we can find the refractive as Ni. Ni can be calculated using this equation, the square root of epsilon I into mu I. For air medium, it is almost is equal to 1. For the nanocomposite medium, we substitute the value of permittivity and also substitute the value of permeability. For normal instance, we find the Ni value. By substituting this Ni value in the matrix form, we can get the 4 matrix element. By getting the matrix element, we can find the value of MH, high and low. Then applying transfer matrix method, we can find the transmission coefficient. T is equal to 4 by T111 plus T2 to the whole square plus T12 plus T1 2 on the whole square. Ta is the elements of matrix. So by using this matrix, straight away we can analyze the photonic band gap. So transfer matrix method, by substituting the thickness value and the refractive index value, we can find the transmitted spectrum of the one-dimensional photonic crystal. Here we are taking n period is equal to 5. Only 5 sets are there, and then magnetic field applied is 10 oersted, and then the fill factor equal to 0.1. Fill factor equal to 0. So we are doping silver in the EG material, ytterbium Garnett material. So by substitute for a filling factor of Fu equal to 0.1, we can, using Maxwell-Garnett equation, we can find the permittivity of the whole composite medium. So so in that, the fill factor is more important. So when we increase the fill factor, everything will be changed. So for the fill factor P equal to 0.1, we get this transmitted spectrum. Almost in this spectrum, when we analyze, there are some 5 gaps, photonic band gaps, from actually frequency range 0.5 to around 0.9 gigahertz. We have a band. Then 1.3 to 2, we have another band. Like this, we have 5 bands are there for P equal to fill factor equal to 1. When we increase the fill factor to we can have other forms of photonic band gap. See here, we have 1, 2, 3, 4, 5, 6, almost 7 band gaps are there. By changing the fill factor, we can analyze the transmission spectrum like this. We can get it. Like this, we can increase other factors also. 1 minute. So it is for another fill factor. See here, the photonic band gap increases from 0.01 to around 4.5. So for all these frequency range, for this frequency range, there is no propagation. Transmittance is equal to 0. Everything is reflected. So now by tuning this, we can achieve some the band gap increases. So by changing the fill factor, we can get this type of figures. So once when we tune, this is for P equal to 0.4, fill factor equal to 0.4, we can get this type of band gap. Such an enlarged band gap. This is actually used for so many factors, for sensors and other applications also we can use. But here we are using for solar cells applications, because solar cell in the anti-reflection coating, we need reflective layer. Everything, it should be reflected. It should not be reflected, it should be absorbed. And also DBR, distributed black reflector, everything should be reflected. So for this purpose we are using. Now there is a comparative chart, how the photonic band gap changes. If we have a fill factor 0.1, we have the photonic band gap around 6 gigahertz. If it is 0.2, it is 3 gigahertz. 0.3, it is 1 gigahertz. Again 0.4, we have seen the figure 3, we have 43 gigahertz. So the whole area we have photonic band gap occurs. 0.5, it is 50. 0.6, it is 40. Like this, according to the presence of materials, it may be changed. Now, number of periods. We can also tune the photonic band gap with number of layers. First, in the first trial, we have used for 5. Now, when we increase the number of layers, what happens to the photonic band gap? So here, by varying the number of layers, actually it starts from around 27 gigahertz, then it goes to 40 gigahertz for a number of layer of around 8 to 10. Then afterwards it will make a constant. So by varying the number of layer also, it will like that. Afterwards, if you go for around 100, it will be around 40 gigahertz. There is no change. We have pointed out up to 22 or 20 periods. Now, when we increase the applied field, the photonic band gap also increases. Photonic band gap here it is given in the terms of nanometer, but actually in the initial period, only there is variation, but afterwards when we apply, initially we have applied for 10 worsted. Now when we go for higher, there is a fluctuation is there, so I didn't show that fluctuation, but afterwards it will be constant. For 200, 400, 600, 800, 1000, it will be constant. The photonic band gap is constant. So conclusion: the tuning of photonic magnetophotonic crystal is studied by varying number of layers. The applied magnetic field and the filling factor. It is found there is no remarkable change in the width of photonic band gap by applying magnetic field. But other factors, fill factor, can give the reflectivity changes. Therefore, we can use this for this photonic band gap for solar cells. Solar cells, we need intermediate reflect layer. For that only we are using this, and also we can also use this for anti-reflection coating and also DBR to localize the light inside the crystal, inside the solar cell. Hence, to increase the efficiency. If the light is localized inside the solar cell by some means, by using this magnetophotonic crystal or other photonic crystals, we can reduce the reflection. In the distributed black reflector, we can increase the reflection. Then in IR layer, here this is main purpose is to use intermediate reflective layer. So here there only reflection is possible to create more electron hole pair. Therefore, we can increase the efficiency of the solar cell. Thank you very much. Thank you for your hearing.
Thank you, Dr. Joseph, for your presentation. So any questions from anyone?
Yes. Good morning to everyone. I have 2 questions.
Okay.
2 questions. The first is, please, Please, the presenter, what explain the fact that the transmittance reduce with the frequency? This is the first question. And the second one,
first question what reflect?
Yes, please. The first question, are you hearing?
Yes, I am hearing.
What represents or what explain, please? What explain the fact that the transmittance reduce with the frequency?
Okay. Actually,
okay. And the second one, what represent the period here? Is that the time that the photon time taken by the photon?
Second question is what?
I'm going to give the second question. Can I go ahead?
Oh, yes.
What represent? Yes. What represent the period here? Is that photon band gap or what?
It's not audible, but anyhow,
Hello?
I understood the first question. What changes the transmission or reflection? Is it?
What explain the fact that the transmitter use with the frequency? That's the first question.
What? Actually, the transmission, reflection, everything is based on the arrangement of photonic crystal, the alternate arrangement of high and low refracting the photonic crystal. Actually, we have in some cases we have total internal reflection is there. When a light passes from a denser medium to rarer medium, then the angle of incidence, then the reflection may be possible. Here, when we arrange alternately high and low refracting material, then the light suffers reflection as well as transmission. In one cases it's reflections. So the combined effect after when we have constructive interference, then we have all are reflected. In some cases, when we have restricted interference, then there is a transmission. I think that also depends upon the frequency also. So based on the frequency, we can change that. We can consider this is that actually affects the optical properties. Actually, we know that the dielectric constant depends upon the frequency. Epsilon is based on k, omega. Therefore, the frequency, everything is frequency dependent material. I don't know what about the second question. Actually, if it is clear, I can explain. No problem.
Okay, no, the first question is okay. Let's now go to the second question. Okay, the second question is that what represent now the period here? Is that the time taken by the photon to return to the band gap or what?
Is there any return to photon?
To return to the band gap.
Band gap. Okay. It's not possible, sir. Actually, for a particular
because you study you also
photon will not return back. In the photonic band gap,
okay,
actually,
it's okay.
It is reflected. That's all. In some other cases, some other dimensions only, in that area, transmission is possible. Here, it will not come again. Therefore, we can call it as a photonic band gap. Thank you for your questions.
Okay.
Thank you, sir.
Okay,
thank you very
thank
much.
You for your, thank you for.
Thank you, Dr. Joseph, for answering the questions. So, anyone else have any questions? So, no questions. So, thank you once again for your presence and presentation.
Thank you, madam.
Okay. Yes. Okay. So, our next presenter is Dr. Samene Birzandi. Hello, Dr. Samene. Are you ready with your presentation?
Hello, yes, I'm ready.
Yes, so our next presenter is Dr. Samene Birzandi from Amir Khabir University, Iran. And the title of the talk is Localized Plasmon Resonance Enhances Trapping of Gold Nanorods. So I'm going to make you the presenter. Yes, so please share your screen with us. Yeah, perfect. We can able to see that. You can make it a full screen. Yeah, you can click on from beginning.
In this talk, we are going to talk about how localized plasmon resonance of the trapped AU nanoparticles could enhance its trapping force. This work is done in American University of Technology at Optical Metrology Lab. Optical trapping have several applications in chemistry. They help in controlling and manipulating nanoparticles, and also they help in building complicated structures such as nanorings. Also, it's helpful in observing the photochemical behaviors of nanoparticles. In physics, it helps in observing fundamental physics and on-edge physics. Also in characterizing optical properties of nanoparticles. It also has a new application in simulating quantum effects for trapped atoms and smaller particles. Also in bioscience, there are several applications for optical trapping of the biosamples like red blood cells. It helps in moving and changing the particles in several applications. It also helps in characterizing red blood cell and white blood cell for finding diseases, or also it helps in optical change of IO structure like DNA, and it has also another application in biochemistry in drug delivery to the cell, and also drug discovery observing. To cover the optical trapping bases, we should start with how light could apply force to the nanoparticles and particles of the same size. It depends on the gradient intensity of lights. What happens is that when a particle enters optical path of light, we observe that particles move toward the center of the focus point of the trap and focus point of the beam. For example, if the particle is it's away from the plane of the trapping, it's moved toward the plane of the trapping, and if it's in the plane but it's off center from the center of the beam, it's moved toward the center of the beam. In a typical setup, we have a laser beam, a very well collimated laser beam that enters a beam expander. The diameter of the laser doubles with the beam expander with the double lens, and it enters a microscope objective lens to focus on the sample. What we have is it's a sample that it's a nanoparticle dispersed in the water or oil solution, in our case in water. In this solution, it's covered with the vacuum grace for preventing from evaporation during trapping, and the two sides of the trapping is covered with the two thin glass with 0.1 millimeters with 0.1 millimeters and it's sorry, it's the scattered light from the trapping side enters the condenser lens, and the scattered light then enters to the mirror, and from the mirror it's reaches an object and lens, and this lens focus light to the quadrant for observing the movement of the particles during trapping. There are several shapes for the nanoparticles, and it's for going to the bio and for going to the atom trapping, it's changed the size of the particle and also the wavelength that we could use for trapping the nanoparticles, and less than 10 nanometers particles. What we are showing here is that the size of the particles is dependent on the the size and the wavelength of the laser that we are using for the trapping the target molecule or particle is dependent on the nanoparticles that we are using. Optical trapping force is the force that applied to the particle when it enters the trapping site. As you can see, the nanoparticles, it's a nanowire nanoparticle, and when laser is on, it aligns toward the center of the trap, and it's aligned in a way that it cannot see the gradient of the intensity, so it's going to the center of the beam. The trapping force is usually determined with the trapping stiffness. We determine a stiffness force or an spring constant force. It's with the name K, Kx or Ky in two directions. What we are doing here is that we equal the movement or Brownian motion of the trapped particle with its potential and its movement inside the trap. As the particle moves inside the trap with Brownian motion, we use the quadrant photodetector. As you can see, the quadrant photodetector have 4 detectors that determines that which part of the quadrant is illuminated with the trapping beam, and having different voltage for different position of the optical beam, we could determine the trapping movement during the trap and measure the potential of the trapping. What you can see here is the displacement of the particle during trapping during 0.5 seconds, and power spectrums of the changes with frequency. These two determines how well the particle is trapped, and we could measure the stiffness or our first criteria for determining other specification of the trap. Here we showed 2 forces that apply to the particle during trapping: a scattering force and gradient force. These 2 forces move the particles in 2 different directions. A scattering force is responsible for in-axis or Z direction of the trapping, and gradient force is the most dominant force in plane of the trapping. These forces are very much dependent on the trapping power and also in particles temperatures after trapping. What we also consider responsible for the stability of the trap is the optical properties like refractive index and absorption of the trapped particle and its size and its shapes. That determines which regime we are in and which formula we are using for determining the optical force. Localized scattering plasmon resonance is a well-known phenomenon that happens for metal nanoparticles. What happens is that in the presence of the electric or electromagnetic field like light, its conducting electrons are polarize the nanoparticle and enhance the coupling of the light inside the nanoparticles, and the nanoparticle act as a micro or nano, depending on the cell, on the particle size lens, and we have a much better coupling, and as a result, much better trapping in optical trapping force. This effect is usually used in two ways in optical trapping, known as plasmon optical tweezers. What they do is they use the nanostructure plasmons for trapping biosamples like cells and microcells or microorganisms, or use other photothermal plasmonic effects like shining light to the surface of the AU or AG that we are using, and also with heating, attracting particles inside the trap. The first regime is a little critical based on the heating that is caused with the absorption of light with the nanoparticles, as usually enhanced with the plasmon effect. And the second effect is usually used for biosamples that are more sensitive to the heating of the sample. Here we are seeing the plasmonic structure for enhancing optical trapping. Usually an structure is used to enhance the optical field inside the trap, or a nanohole is used for creating a field enhancement inside the trap. Also here you observe another way for creating a plasmon trap. But what we are doing in our case is a little different, because we use the trapped particle as a plasmon resonance effect. Here also we have a photothermal plasmon resonance. We use here, they use here an AU surface for heating, and they shine light to the surface of the metal, and the photothermal effect attract the nanoparticle in the area of the metal surface. Different particles are or different material are used for plasmon resonance. AU and AG have an advantage based on the higher effects. They provide lower power, higher stability, and they have a unique morphology that will lead to better field enhancement. They also have low chemical stability for AU because it's easily oxidized in biosamples. There are several materials that use as a alternative like Cu and graphene. Graphene has a higher transmittance in visible light and have a good plasmon resonance, and it's a recently investigated particle. To measure the plasmon resonance for the AU nanoparticles, we usually measure their absorption and the transmission in the visible to infrared range. What we are doing here is that we are using the AU nanoparticles in the red detuned resonance based on our laser wavelengths. Our laser is used in 975 nanometers. So we are actually here in the spectrum, and we are far from the resonance of the AU. Plasmon resonance is also dependent of the size of the particle compared to the wavelength of the light, and it's usually change the peak of the spectrum based on the size of the particle comparing to the wavelength. So here we are showing the position of the particle changing with the diameter, which determines that we have a much stable trapping in this wavelength for 100 nanometer VS time. We use in trapping setup, we use a Shake-Hartman because we want to measure the point speed function of the laser in the trapping site. But we usually use a quadrant photodetector to measure the movement of the particle during trapping. But using this method, we are able to measure the point speed function and its changes during trapping. Here is a schematic of our trapping. We use a well-collimated laser. It enters the beam expander and it's reflected with two steering mirrors and enters the objective lens and focus inside the sample. And the scatter light is collected with the condenser lens, and the light is reflected with another hot decorative mirror and enters the Shake-Hartman sensor for measurement. Shake-Hartman sensor is a CCD in the front of the micro lens array. The distorted wavefront measures, sorry about the picture, measures the displacement of the spot of light based on the reference light, and this displacement determines the curvature of the wavefront. The collected measurements determines the wavefront of the incoming light. Here we have PSF. How we measure the PSF is that we measure the Fourier transform of the incoming light, and with using this formula we could measure the point speed function of the trapping. We have two measurements to remove the phase unwrapping in the measurements, using the difference between these two measurements, we are able to measure the PSF. As you can see, we measure the first we measure the optical trapping pad of the particle or trapping size of the particle, and here we have a 0.2 micrometer for the AU nanoparticle, and using this we are able to measure the point speed function in the plane of the trapping, and using the gradient of the point speed function we are able to measure the force that is applied in the trapping. And we have based on the fact that the plasmon resonance could change with the power of the trapping beam, we change the power of the trapping beam, and what we observed was a different response. But before that, we measure the different particles PSF to demonstrate the different effect of the plasmon resonance for different particles. And after that, we increase the trapping power for the AU nanoparticle, and we observe that with increasing the power of the trapping, we have a much sharper trapping point speed function. And based on the fact that the force depends on the gradient of the intensity, we have a much higher force to the trapped particle. Here we measure the stiffness to be 2 piconewton divided with micrometer, and we have a polarization for the AU particle to be 60 multiplied 10 in the power of minus 17. As you can see, we also measure the trapping force, and it's much confined for the higher power. In summary, we achieve a higher trapping stiffness with increasing the power of the trapping. And also we demonstrate that coupling of the light depends on the trapping power. We also establish a method for measuring different response of the nanoparticles for different wavelength for using trapping nanoparticle, for using trapped nanoparticle inside biosamples. It also suggests that to use a laser in near resonance to benefit from nonlinear effect without thermal effect, or basically shining a visible laser to the trapping site to increase its plasmon resonance for measuring inside the biosamples. To that, I like to thank my supervisors in PhD, Professor Dimitri Budke for 1 year in mines, and their Khosrow Madanipur for their collaboration for my PhD. Thank you.
Thank you, Dr. Samane, for your presentation. So any questions from anyone?
Hello?
Yes, hello, Dr. Bernard.
Thank you. I will first congratulate the presenter for the kind of presentation. Please, I want you to go back to page 21. I want to ask a question on page 21.
Sure.
Exactly 21. Yeah, please. I want to know the representation, the meaning of the physical meaning of this negative part on the second figure.
You mean yes, this right figure demonstrates the force in the trapping side, and as you know, the trapping force is directional toward the center of the trap, and this is a demonstration of the force around trapping center.
Hello?
Hello. Did you hear my answer?
Not clearly, not clearly.
No. What we have here is the trapping force around the center of the trap, and as you can see, we have the maximum trapping force applied around half after the trapping site. What we have is usually around this number, and this is a demonstration of the sharpness of the trapping force. As much sharper this trapping force is, we have a much higher localized intensity and much higher intensity and gradient intensity that could will lead to higher capability and higher efficiency of the trapping.
Okay, thank you very much.
So thank you, Dr. Samane. Is there any questions from anyone? So no questions.
Thank you very much.
So So our next presenter is Dr. Bernard Donfack from University of Shashank, Cameroon. So the title of the talk is Cumulative Effects of Laser and Spin Orbit Interaction on the Thermal Properties of Quantum Pseudodot. So hello, Dr. Bernard. I'm going to make you the presenter. Yes. So can you please share your screen with us? Hello, Dr. Bernard. Hello, am I audible to you? Hello, Dr. Bernard. Are you active with us? Yes, we can able to see your mobile device. Your voice is not audible, doctor. Hello.
Hello.
Yes, so can you please share your screen with us?
Hello.
Yes, perfect. Please open your presentation.
Yes, I'm trying to share my screen very soon.
Yes.
Can you see my screen?
Yes, so you can open one by
Hello.
one slide. Yeah, we can able to see. Yes, you can start your presentation.
Okay, thank you for giving me the possibility to present this work. My work is on the cumulative effect for spin orbit interaction and laser field on thermodynamic property of quantum pseudodot. This work is structured as we start by an introduction. After introduction, we present methods and model, result and discussion, and end by a conclusion. Let's record that quantum dots are small devices that contain a teeny drop of free electrons. Their dimension are between nano and few micron. The size, shape, and number of electrons can be precisely controlled. Unlike atoms, however, quantum dots can be easily connected to electrodes, are therefore excellent tools to study atoms. You can see here the different steps to obtain the quantum dot. You need indium and arsenide, and then you can depose all that on the substrate called gallium arsenide. After that, as you are working in electrons, you think here that we can also work taking account the spin and their interaction with the magnetic moment. In recent years, much attention has been paid on high intensity storage devices to better understand the utility of spin, and design of these devices based on small molecules can be necessary to extend our study on the degree of freedom of spin and their coupling interaction. That's why we have here in account the interaction of spin and magnetic moment to obtain spin orbit interaction. This can happen if you apply an external magnetic field on spin, which first have their initial direction. The effect of magnetic field will act on those spin and then change the direction of the spin. This can be seen in the next figure. The choice of our subject is motivated by many applications of nanostructure in semiconductor. Since one of our project is based on the modification of solar panel to integrate quantum dots and take in account the spin of the spin interaction. Since the spin have the capacity to create the more accessible state, we also think that we can take in account those spin and this can help us to increase the efficiency of solar panels in order to use them in our house and also on some industry. The next step now is our problematic. What is the impact of spin orbit interaction on the thermodynamic property of quantum pseudodot? What is the impact of spin interaction, the spin orbit interaction and variable magnetic field can be used, it's called here laser, on thermodynamic property of nanostructure? To answer those questions, we have some objectives to evaluate. Our objective, the main objective here is to evaluate the cumulative effect of spin orbit interaction and the laser on thermodynamic property of quantum pseudodot. Use this objective is also attained using the specific objective. Use the Trailway function to solve analytically the Schrödinger equation in order to obtain the ground state energy. Use the Thales formalism to derive the thermodynamic quantity of quantum pseudodot. Use the MATLAB application to simulate our result and discard the result obtained. After now, give the introduction. This is our Hamiltonian used to formulate our system. You have here H and A0. This H and A0 here, A0 is given by this expression, and H spin orbit interaction is given by that. Using this potential given equation 204, which help us to move from quantum dot to quantum pseudodot, because the difference between quantum dot and quantum pseudodot is just the potential used. If we use an harmonic potential, you are going to have now quantum harmonic pseudodot. Using now our Hamiltonian, those two Hamiltonian, you're working in cylindrical coordinate in order to follow the shape of our system. The Hamiltonian H0 is given in 206. Using now the wave function given in 208, which is here, we can transform our Hamiltonian, the next Hamiltonian H0, having in a 200 in equation 200. Where alpha, beta, and gamma are given in equation 10, equation 210. The next step is to calculate now, make some transformation to have an obvious equation that we can easily function using H0 and the wave function given previously. So the energy E0 is given now in equation 214. After now obtain the equation, this is the different step follow to solve this equation and get the energy in equation 214. After this, we are going to solve the energy linked to the spin orbit interaction part. After changed our energy, you have now the cylindrical coordinate of spin orbit interaction given in equation 216, where sigma x and sigma y represent the Pauli matrix. So we have here in equation 215 the Schrödinger equation linked to the spin orbit interaction part. In equation 216, transformation of this Pauli matrix in cylindrical coordinate, and then in equation 218, we have the energy linked to the spin orbit interaction part. To have the total energy of our system, now we need to take the energy obtained with the H0 and the energy obtained with the spin orbit interaction part. After obtaining the energy, we can now calculate the thermodynamic property of our system using the Thales formalism. Our function, the partition function, is given now in equation 94, where E plus and E minus represent the energy of the two states of spin. E minus is the spin down and E plus is the spin up. Our entropy is given by equation 91. We will help us to evaluate the rate of disorder in our system. The internal energy here is given by equation 92. The free energy will help us to evaluate the exchange energy between our system and environment. Is given now is in equation 96. The energy need to change the temperature in our system. Related now the heat capacity given now in equation 90. You can equation 95. After calculated the thermodynamic property analytically, we are going to use MATLAB application to simulate our result. The frequency of laser for different value of principal quantum number. We observe here that for lowest value of the frequency of laser, we have the highest value of energy. We mean that as the frequency of laser increase, the energy will also decrease because the laser will reduce the motion of our particle. In the question, in the next figure, the one right, we evaluate the variation of capacity as function of external number, extensive number, please, for different value of a spin of interaction. We see here for low value of the extensive number, you have the highest value of heat capacity. What means we need the energy needed to change the energy for low value of K will not be enough. We calculated here the next figure. The next figure gave the variation of heat capacity as function of temperature for different value of alpha, and our alpha was the spin orientation and the frequency of laser. We saw that we need to change the energy of the system, to change the temperature, please, of the system. We need highest value of frequency of laser, but low value of spin orientation. So our system can store more energy for lower value of temperature or for highest value of temperature, but we accumulated two value of two parameter of spin orientation and frequency of laser. In order that if you need to increase the temperature, we can maybe either need much value of highest value of spin orientation or low value of frequency. So those two parameters are very important to change the energy of the system or to vary the temperature. If you need the system to be hot or to cool the system, you can either increase the value of spin orientation and decrease the value of frequency of laser. So the both parameters are very important to exchange or to create the system. To increase the rate of heat in the system. We calculated the free energy of the system. You check as function of the value of the frequency of the heat energy, please, as function of the intensive number for the value of spin orientation and frequency of laser. We discovered that we have the highest, the non-periodic system, but this depends on the value choose of the value choose for spin orientation and the frequency of laser. As we said before, those two parameters are very important to control the exchange energy between the system and the environment. If you need to lose some energy as a heat or to lose some energy as thermal energy, we need to increase maybe the value of spin orientation or the value of frequency of laser. In this case, we see say those two parameters in the box figure. Since the box figure are storing the variation of free energy as function of frequency of laser and spin orientation, the box figure are explaining the same thing. So if you increase or decrease the value of spin orientation or the frequency of laser, we can control the exchange energy between our system and the environment. We now study the of Thales entropy, and the Thales entropy as function of in the first figure as function of the amplitude of laser for different value of spin orbit interior of different value of spin-orbit interaction. As we said, the spin has it has the capacity to create the more accessible state. We are now working on the integration or the implementation of this spin and quantum dot on solar panel. So if we take in account the spin on the solar panel, we can create more accessible state. Create more accessible state now means that we can add the efficiency of solar panel to store the energy. So now take in account the spin, the entropy is just because in our previous work we work on the effect of spin interaction on the thermodynamic property of quantum pseudodot. We discovered that the result was good, but there was too much rate. Now we ask ourselves how to reduce the rate of entropy. Since the laser has a system, we now cumulate those two parameters. So one will create the spin of interaction, will create the accessible state and increase the capacity of the system to store the energy. And the laser now will come and stabilize the system, decreasing the rate of entropy. This is why cumulating the two effects in the system. So we can see the variation of the spin of laser, the frequency of laser. You have for the low value, you have the high energy, but when the thing is increasing, the entropy is also decreasing. In this work, we investigated the cumulative effect of laser and phenomena interaction of a property of quantum pseudodot using the Thales formalism. Why use the Thales formalism? We chose to use the Thales formalism here because when we used in our previous work the Bosman-Gibbs formalism, we discovered that we were working in the whole system, even the unaccessible state. Since the Thales formalism now is based on the accessible state in the system, we should have now we are going to use the Thales formalism. Since from the result obtained, one can conclude that the spin-orbit interaction affect and create more accessible state, but increase the rate of entropy. Means why we find useful to accumulate the spin-orbit interaction and laser field since laser is a decreased parameter of entropy. We also in the looking for a partner or a laboratory where you can carry the experimental part of this work to make them useful to ourselves and to our community. Thank you for your kind attention.
Thank you, Dr. Bernard, for your presentation. So anyone have any questions? So no questions from anyone. Thank you once again for your presence and presentation. So as Dr. Manojit and Raja Sheikh has not yet joined, so we will conclude the day 2 webinar by here. So by this we came to our day 2 webinar as well. I would like to thank all the attendees and participants of day 2 and thank you for making it a successful one. So we'll send you the certificates to your email in a short while. Please do check it in spam or junk. Hope you enjoyed this and gained some knowledge from the session. And we'll be very glad if you could share your opinion or feedback with us through email. Thank you and have a nice day.